Okay, so this is how you would get the solid of revolution for y squared equals x squared plus 1 bound by x equals 0, x equals 1, revolved around the y-axis. Sorry. So you can see it's just that shaded in part over here. It does help to kind of have an idea of what that would even look like. So this is kind of like a front view on the left-hand side of what it'll look like. And then kind of like on the right, I have a top front view of what it looked like. So it's pretty much a big cylinder, except it's missing this kind of, it has this parabolic cutout, which is essentially all this empty space over here getting revolved. So you can think of it as like a sort of satellite dish shape where everything in the middle is cut out, but then all the rest of this is all solid. I've got kind of just further diagrams to help on with what's going on. First, this is just like the idea of cylindrical shells. What happens is you've got like this outer shell over here, and then this inner shell over here, and you're going to subtract the volume of this outer one and the volume of this inner one. So you're subtracting the inner one from the outer one, and you're left with just a husk or a shell. And this is actually what you'd be left with. I've said this is just the back view. This would go all the way around, but that kind of doesn't help you to see what I want you to see here. You've got this width, which is basically just the differences in radii between the two cylinders. You've got these heights, and then the actual radiuses, or radii themselves. Now, when we're finding the exact volume, we're going to be integrating. So this is going to be infinitesimal. It's going to be infinitely thin shell. And so the difference in height here is going to be negligible. And you're not going to think about the differences in radiuses. It's kind of just the average radius, or just the radius from here to this point right over here. Okay, I think that's good enough. You can see that this part over here is slanted down. That's supposed to represent the slanted down parts. The slanted down parts all along there, and then I guess the slanted down parts through here. You can see that the h, using this formula over here, which is just 2 pi x f of x dx integral from a to b, that should give you the exact volume by cylindrical shells. Now, the x is just the radius, or the average radius. That's the distance from here to here. F of x is the height, and in this case, it's just going to be the y value. So for if the distance from here to here is, well, in this case too, it's going to be x. And for this x point, what is that y going to be, or the height? The height is going to be the y. And from our formula, we know the y is going to be x squared plus 1. So we've got h is equal to x squared plus 1. The radius is equal to x. We just plug those into here, and we get the volume is equal to the integral from 0 to 1 of 2 pi x squared plus 1 dx. This over here is just a basically smaller inner shell. So if you had this 1 dx, that you'd add up this one shell, you'd add up another shell and another shell and another shell and another shell and another shell, and you get smaller and smaller and smaller. So this is one of the smallest shells, and that kind of represents this bit right here, this bit right over here, and then the two cylinders that get subtracted through. So even in this case, you can see from here to here would be our descent dx from the center to the cylindrical shell is a distance x, that's our radius. From here to here is going to be f of x, or y, which in this case is x squared plus 1. So everything still holds over here. If we evaluate this, we're going to get 3 pi over 2. That is it. That's it.